I'd highly recommend viewing this episode on YouTube rather than as an audio podcast because there are many visual examples presented. Hello and welcome to the Color Mentor podcast. My name is Paul Hanrahan. I'm a colorist, originally from South Africa. Now I'm based in Taiwan. On this podcast, I'm going to be talking to people who have mentored and inspired me on my color grading journey over the years. So welcome to the show. If you'd like to learn more about color grading, you can head over to my Patreon. It's called Color Mentor at patreon.com, and it includes basic skill training all the way up to full coursework on various topics. I also offer one-on-one mentoring for those who want to refine their craft further. But without further ado, let's get on with the show.
In this episode, I chat to Menno Dreischor, who's a chemical engineer based in Amsterdam. His company is called TIPb, and they offer various engineering solutions across a wide range of industries. Menno's interest in film led him to develop an algorithm that initially helped with the restoring of faded film scans. It analyzes pixel distribution of a supplied source and target image and generates a LUT that does matching between the two. It is currently in a beta testing phase and has many potential applications from restoration, shot matching, and creative look design. In the broader context of the film industry, I thought it was important to mention this factor, is that this and other tools are part of a general trend to automate and streamline various processes in the production pipeline. There are many laborious color grading tasks which could benefit from automation, such as conforming and shot matching. But having said that, I do feel that to simplify the whole task, from grading to creative collaboration and all other tasks, to an automated function that's been scraped from historic examples, I think would be a dire future. Menno's matching algorithm uses distribution matching of input images only, rather than machine learning based on a vast library of training data. It feels like a new way of looking at the picture formation and image analysis, so I feel that it does have several beneficial potentials, but it's very much at its infancy, and questions around final user interface, exactly how it will be implemented, online or offline, obviously still to be decided. He also has a second algorithm which tries to predict the visual cognition aspects in any given image. So, such as things like simultaneous contrast, assimilation, the watercolor effect, and many others. In the interview, we discuss both projects and their potential applications, so let's get on with it.
So, Menno, it's so nice to have you on the Color Mentor podcast.
Thank you. It's so nice to be here.
Yeah, we've been chatting online a little bit, and very fascinated to get involved in your project. And I was very happy that you could give me the demo this week, because it's really, I don't want to like spoil it in the first sentence, but it's kind of, I had some preconceived ideas and I thought, oh, it's going to do this. And then there were some areas where it did and some areas where it didn't. And I thought, oh, okay. But then the longer I thought about it, I think it's going to have quite wider effects on our industry and the way we work. Because in one sense, it's another way of processing the data and accessing the data and manipulating the data that we don't really have access to in the current tool. So yeah, I think it's very exciting, and just as a one-liner, I'd say it definitely does have a future.
Well, that's good to hear.
Yeah, I mean, well, it's all, we can talk about the details, how it's implemented, and is it standalone or is it incorporated into color correction software? But anyway, before we get into that, could you tell us a little bit about your background? I mean, are you a chemical engineer by training?
Yes. So I studied chemistry in Amsterdam many years ago. So this was 1994 till 1999. So that's
right.
I've almost forgotten everything that I've learned back then. Yeah, and then I had a couple of friends in the building on a different floor who were so my part. So I at first I went to do a project for Shell, which was just kind of a chemical engineering type project. And then I decided, maybe it's nice to do a PhD. So in the end, I did a PhD in a computational physics group, but I was on the theoretical side. So while everybody else was doing computer simulations, I was mostly involved with trying to kind of build simple abstract models for polymers. So you probably know what polymers are.
Heard of it, but
The building blocks for plastics, essentially. So all plastics are polymers.
Right.
They are very long chains of molecules, and this gives them very specific properties. And so I spent a lot of time kind of going back to the theoretical side of things, really old theories that were still being used, but then giving them kind of a new lease in life.
Right. And then how did you diagonal intercept across to the film industry, which is quite a leap away?
Well, so my two colleagues that I'm working with now, they were more on the data side. So they did a PhD in chemometrics, and chemometrics is kind of the everything to do with it has a very heavy statistical component.
Right.
So and this involves going to factories, analyzing the data, seeing if you can detect reasons for inconsistencies, quality control, all that kind of stuff.
Mm-hmm.
And the film industry was kind of a side thing, because I was kind of well, I wouldn't say involved, but I knew the people that were working on the unofficial Star Wars restorations.
All right.
The whole theatrical version debate. And they were, so one of the challenges, of course, were they got these old film scans from all kinds of places, people that owned old film prints.
Mm-hmm.
and the like. So then the challenge became, often these prints would obviously not have very great color, because they were, depends a bit. If it was a Technicolor print, it obviously had a lot of color, but for example, a lot of these prints were, for example, The Empire Strikes Back, I think was filmed in an area that had probably about the worst kind of film that existed, so it faded to red like really quickly.
Mm-hmm.
So one of the challenges was, okay, we have the original version, but it doesn't look very good this way. So what can we do as amateurs to kind of make it look more acceptable? And the people obviously got free versions of Resolve and started using cursor adjustments to get it to look a little bit better.
Right.
And then at some point, I'm not really sure what prompted it but I came across some papers on color matching and an interesting kind of way that somebody did it, and I decided to kind of implement a version of that algorithm to kind of help people to make it easier to kind of to automate. So and the idea was, if I have the exact same shot from, let's say, a DVD,
Right.
and I have the film print, I can match the film print to the shot. I can create a LUT, and then I can kind of color correct the entire print to kind of look acceptable, and then you can make your own kind of adjustments here and there to make it look, because everybody was really, let's say, obsessed with the idea that we wanted it to look like a Technicolor film print, which obviously has a very specific look to it.
Right.
So this is kind of where it started. So it kind of started as a bit of a hobby at home, in discussions, helping people kind of get some tools to as amateurs be able to get some reasonable results. And as the group grew, obviously some colorists came in, and the overall results became better. But yeah, that was kind of the start of the way I got into film and building kind of algorithms.
Your weapon of choice is Matlab, right? Is that basically the underlying, right? Okay.
As a company, we worked with Matlab kind of since university, and well, obviously now Python is kind of, I think, for most people the software of choice, because it's freeware essentially, or at least it's an open source environment.
Yeah.
But Matlab still has some advantages from a company perspective, because they have a lot of toolboxes. The code that is being developed is obviously checked by Matlab itself, the MathWorks, the company that uses Matlab, and it still has a lot of. Matlab had I think from the first day, is kind of this file exchange where people could write their own code and then share it with others.
Right.
So this was kind of a big thing, because it created a lot of opportunity, because you build something and you don't have to kind of program everything from from scratch. And today with the coming of ChatGPT,
Right.
you can do even more in terms of coding because one of the areas where ChatGPT is actually pretty useful is in writing code and
Right.
quickly testing things out. So
I'm wondering if other than the fact that chemical engineers, chemists had to be involved in the film processes of old. I also noticed that Jean Pablo Zambrano, who's also a very prolific young code writer for color, he's also a chemical engineer. So I've got a theory here. What's the connection? Anyway, but so you have a company now, TIPb, right?
yes, correct.
Do you still have links to the University of Amsterdam, or are you essentially a free company now and just in the commercial world?
We have some link to the University of Amsterdam in the sense that we work together with the University of Amsterdam. So, for example, today we work a lot with the forensic department in the University of Amsterdam because we developed this analyzer that can detect drugs essentially.
Oh, okay.
So so the idea is that you have an unknown powder and you want to know what it is. It's white. Well, it could be powdered sugar, of course.
Right.
It could also be something different.
Right.
We got involved in this a really long time ago. So I think already almost 20 years ago, we first made our first kind of steps this way. And over the last couple of years, we kind of redesigned that whole concept. And so, that was done to a certain degree with this cooperation with the university. But we don't have any direct link with the university. So we're a separate company now,
right.
And have been for 20 years. But we do cooperate a lot with universities, but also with the Dutch police, for example, and other partners Let us say we're just like four people, so you need some outside knowledge, and you're not going to make it just by yourself. You can't think everything.
Just out of curiosity, these detection systems, are they also optically and light spectrum based?
For near infrared based. So you have the infrared area, of course, which is well known because it's used to detect or make all kinds of identification on specific peak locations in the spectrum, but near infrared is at a different wavelength area, and it's a little less defined. So you get peaks, but they're kind of overlapping, and so you can't make the kind of identification that you do in infrared, where you can say, okay, I have a peak at this many nanometers, and it represents this component. So you have to use statistical methods to kind of essentially use calibration to build models to relate a near infrared spectrum to a component or a mixture of components. So that's it's in the light spectrum, but it's outside of the visual spectrum essentially.
So each substance has its fingerprint, and you would look for that fingerprint within.
Exactly. And then the challenge becomes that for example in the drugs case, if you take a drug like cocaine, it's cut with other agents essentially. So you almost never on the street get pure cocaine. So it's like 20 or 30% cocaine with something else. And so the challenge becomes, how do you identify the combination of components where you get a fingerprint, but it's not really and then there are a lot of different ways to do this, obviously. But this is where we kind of had our unique thing. We built an algorithm that could kind of separate the spectrum into its different components, and then say, okay, it's this component mixed in with that, for example.
Oh, okay, cool. Yeah, that's fascinating. So yeah, it's a lot of Fourier transforms and all that kind of stuff.
Definitely.
Okay, cool. As we turn to the color matching project, does it have a name so far? Not yet, right?
No. It's just I just call it color matching and prediction. Essentially, this is what I once started a thread on the website originaltrilogy.com that was called color matching and prediction when I first started working on this project, and it's kind of how you say grew a bit out of hand after that,
right.
Because for years I kind of had this little app that I gave to people if they wanted it, which just matched two identical shots with different color grades, essentially. But then at some point, I think about 18 months ago, maybe a little longer. I think it was just before COVID when I got a call. I was contacted by somebody from China who had read the thread that I had on the website and wanted to see if we could do something, but then they misunderstood me and they kind of came up with all these shots that were not identical shots.
Right.
And I thought, damn, and what am I going to do now? So at that point, I very quickly started to kind of figure out something which could do non-identical shots, and it kind of developed from there. So at some point, COVID happens, and this kind of all ended. But then after I think a year or so, I decided to kind of put it more on a more, let's say, better foundation, and I kind of worked it out, and that's where how I got here essentially. And at some point, I put it on LiftCam again,
Right.
and started some discussion essentially there, and yeah, so that was kind of the beginnings of this whole project.
Yeah. Okay, so just for people that haven't been exposed to it, we basically run them through the process to say that we have, whether you're matching shots that should be identical, so two versions of the exact same shot, or whether you want to take this look and bring it across onto totally different footage, you have a source, you have a target, you tell the algorithm to go, and then there are various parameters.
Yeah, exactly.
Okay, and then what you walk away with is a 3D LUT that can do that transform for you, and there's some smoothing parameters and all that kind of thing.
Yeah.
This is what's really fascinating. So essentially, it's looking at the pixel distribution as a space. It's a model. It takes the color, all the pixels, and the shape that they form, source for a target, and it essentially does a comparison.
So what if I have to kind of summarize it, and it's easiest to understand for the version with the where the shots are identical, because what it's actually saying, okay, I can kind of take out all the specific location information, and you kind of just look at the distribution of stimuli in the picture.
Right.
And you can do this for both the source and the target. And because the grade is different, essentially, it generally has a very similar shape, specifically for the identical, but it's kind of warped a bit. So it's been shifted more towards red in all kinds of different directions. So if you look at the two distributions, you can say, okay, I can see that there's a certain common component there, but it's been non-linearly adjusted. So how am I going to match those two things essentially? And the way, and this is not something that I thought of. This was in a paper that I read, although I did make some adjustments to it. But the basic idea is that you start with histogram matching, which is kind of the simplest form of color matching that you could do, which is kind of part of pretty much any software program that does statistics can do histogram matching. In a more general sense, just matching distributions, because a histogram is kind of a simplified way of plotting a distribution. But the problem is, because of the complexity of the transformations, which goes in all different directions, so all colors are kind of in 3D space, they don't have to kind of align with red, green, and blue as we see in an RGB space. They can be changed in all kinds of different directions, because it's been done in a different color space, or just generally because you change the saturation. This changes it in a different direction than just changing red, green, and blue in a curve adjustment kind of way. So what happens essentially is you start kind of shaping the distribution to kind of match the shape of the target, but you do this in a rotating fashion. So it's kind of, I kind of picture it like the way you would shape a piece of clay. So you start on one side, you push it together, you pull it out, but then you cannot do it. You have to kind of go to a different direction to kind of pull it again in a different direction, etc. And you rotate this all the time until the shape matches the shape of the target, essentially. So it's kind of like, the algorithm kind of treats the color distribution like a piece of clay, and it starts pulling on it and pushing on it until it kind of has the right shape, essentially. And then the assumption is, if that shape is similar enough to the shape of the same distribution of the target, then the colors in the picture will generally match very well with what you would expect or what you would want.
That's fascinating, because you're quite limited. Obviously, straight RGB histogram is very smooth normally, but it's a way more dimensions. Now, so in the basic, like, exact shot, but different color, it is actually looking pixel to pixel. But in the case where you want the look of Terminator put onto your footage that you shot on your phone, there's obviously no relation, and it's more, now you're dissociating image content with the look, the color space. So are those ones, I think the term is your universal match, are those now not spatial in terms of pixels? There's no spatial pixel component?
Well, even in the original version of the algorithm, there's no spatial picture component.
That's what I wanted to ask you, yeah.
In all cases, it says, okay, I can kind of go to a distribution based, so I kind of, so essentially what happens is I could ideally randomly mix up all the pixels in the picture, in both pictures, and it would still come up with the same result.
My exact question, could I scramble the pixels, keep the values the same? Okay, yeah. Got it.
Yeah, the algorithm sees those two pictures as exactly the same, essentially, which is kind of interesting given that it obviously doesn't look anything like the original picture.
Yeah.
But from a color perspective, this is the way it looks at it. And this is also the only way, I think, outside of really like going towards the kind of stuff that Troy is often, the picture formation, where you really have to know exactly this is a table, right. This is a face, etc. You start to really kind of decompose the picture in its various elements and then assign color to it. But this is not the way that this algorithm kind of looks at the world. And obviously that has some potential downsides, but at the same time, it has the upside that it's really quick, essentially, in the way it can analyze a picture, because it doesn't really need the information of. Yeah. And it kind of opens the world to go towards the situation where you have two pictures which are not identical, because then distribution give you the opportunity to kind of do that as well.
Yeah, it's much broader. So in your theoretical explanation of it, you mentioned that you're almost trying to get you have your parameters P style, P lum, P scene, and P image, and these are parameters in your model. But surely those are, because you don't, the machine doesn't know what is a table and what is it's more just the lighter part, the darker part. So it's very hard to disassociate object from how it was illuminated in the two situations. I mean, are those actual parameters in the model, or are those just like a theoretical understanding of the color space is the same, hence?
Yeah, they are part of the model in the sense that these are the things that are being matched, essentially. So they are representations of the trick is obviously how do you get to those distributions, because they each represent different. So the way I kind of see it is, if you have a grade, it represents kind of the way a colorist looks at the image and the kind of style or look that he wants to give to the image. And I kind of separate that look from its specific implementation in a specific picture. So there are common denominators. So if I give a colorist two pictures of a film under different conditions, there will be common denominators between the two, and we kind of see it, because if we look at a film that's been graded, we obviously see that each shot has its own unique components, but we also see kind of a consistency in there. It's supposed to have a consistent look. It's not going to be some random high saturation look in one frame and then something completely different in the other. So the whole trick is, how can I kind of extract that consistency from a picture in a distribution sense? And then the way I saw it is, there are different levels of this. At the level of the shot, you might say everything is completely linked to the way the picture has been composed, essentially. And in composed, I mean the amount of each stimulus that is in the picture. Right. And the algorithm will assume that if I have a target, it will have the same amount of that stimulus, except it's been manipulated in some way. And then the next level is saying, okay, what if I decouple it from its composition, and I say, okay, it needs to find a distribution that no longer depends specifically on the exact amount of each stimulus in the picture. It can have the same stimuli, but it has a different amount. For example, it's a wide shot, so I see more of the trees, and the girl that's in the picture is now smaller, so her face, so there's less of the facial the skin tones in the picture, and etc. So then you have to find a mathematical way to kind of decouple those things and define a different distribution, which no longer depends on composition, essentially. And that distribution is what I called P lum, essentially. So it's a distribution which no longer has the compositional elements. So it will match a picture which assumes has been shot under the same lighting conditions. But it assumes that well, it's the same stuff, but it doesn't have to be in the same, how do you say?
Quantities, ratios
Yes,
of quantities.
exactly. It's the same ratios essentially.
Okay, this is making a lot more sense. Okay, great. So these are concepts all from a statistical distributional point of view.
Yeah.
It's not like saying, okay, we're doing from a 2D raster image, we're now back propagating into some 3D interpretation of what might have been, how the camera was composed. It's really just from a color distribution and shape of within the color space.
Yeah, and similarly, you can go to another level, which is the what I called p-style, which is or p-loop, you might also call it, and that kind of tries to decouple the lighting element from which is kind of a next step. And the thing is that each of these steps obviously involves more approximation. So the model which matches the same shot is generally the most accurate because it has the most to work with. And each time you remove something like composition or lighting, you make more assumptions and more approximation. So the model becomes more approximate as you go to, but at the same time, it's a lot more, it can handle a lot more different types of situations. So this is kind of the trade-off that you make.
So it's kind of this shaped thing, but now it's moved like into the shadow or closer to the red light or closer to the blue light or overexposed, underexposed.
Each time you're actually saying, okay, everything is part of this big distribution p-style. And if I then add a lighting component to it, you kind of have a sort of weighted way in which you adjust p-style. So the dark elements will, for example, be made darker, and then so the luminance adds an element to it which gives it a unique visual effect under the lighting, and then the compositional element also has then an effect which is again a subset of that distribution. So you're kind of trying to go to higher order distribution which cover more of the color space essentially that you and that is kind of one of the interesting effects is that when you do like we discussed in the Discord server, when you kind of make a collage of pictures, you're essentially doing the same thing. You add a lot of different images together, and you also kind of get a sense of p-style, because there you kind of say, okay, I'm going to average over a lot of different pictures. That has effectively the same effect. And what you kind of see is that all these kind of algorithms converge. If you add enough pictures to it, at some point, it doesn't really matter anymore, except for the shot-to-shot match, but the universal match and the scene match kind of converge together if you use them over a large number of images, because that's kind of the limiting step there, where you say, okay, this kind of captures the style of the movie at its most coarse in the broadest sense, you would say.
Yeah, I mean, I think there were some things online. I'm not sure exactly how it was done, but it was essentially picture every single frame of a movie averaged together and represented in one frame to show you the global. It's like the block universe, but for a movie. Yeah, this is really fascinating. So you put out a term there that was quite interesting. You said luminance independent color matching. So it's like, yeah, there can be these it's like how rigorous you want to be. Does it have to be exact, or does it have to be roughly? I think that this is where I think the tool can have a lot of different implications. The idea that I just had now. So what if I give you a bunch of things? So example, like a neutral LUT, which is just all points equally spaced throughout the cube, and then I do a range of typical operations. So typically, when I do a film, I build a 1D curve like this, and then I do my split toning like this, and then I do my HSL and 3D matrix and all these things like this. And if I fed to each of those to you individually and you analyze those, that would be yet another way of breaking down the distribution of typically in a high contrast film, this is what the S-curve looked like. Or, I think maybe there's room for that additional level of analysis.
Yeah, well, one of the things that because obviously an algorithm does a lot of let's say complex nonlinear transformations, and it's kind of difficult to kind of visualize what it does. So one of the things we were kind of looking at and still looking at is kind of a way of representing that result in a more traditional colorist lift gamma gain manner, to kind of get a better sense of what is the algorithm actually doing, and if it's because one of the things is in a sense so. if the result looks good, so why does it look good? But also, if the result doesn't look good, where does it make an error? Where does it interpret the image differently from, let's say, a person who's looking at the picture, essentially? Yeah. So from my point of view, it's kind of two different ways. One way is obviously that you want to build a tool that has some utility to it. But at the same time, there's also kind of a whole host of research questions, you might say, that pop up.
Yep.
So I've made a whole host of assumptions, some of which will be less problematic than others. You're always simplifying the world, essentially, which is also kind of when we get to the other part of the discussion about cognition. They have kind of the same thing. So what information do you keep and what information do you drop? And you make kind of very conscious choices about this, because you cannot really model everything, because that's not a practical solution, especially if you want to get a result within a reasonable amount of time. In my case, I generally have a patience which lasts, let's say, a few minutes. I don't have, I'm not into the whole, I'm going to wait through. I had colleagues which at university who built models, and then they had to put it into kind of this big, they had this computer network, and then they had to wait like 3 weeks.
See you in 3 weeks,
yeah, for the results to come out, and only then they could see, crap, I used the wrong wrong input. I have to do it again. So, and I don't have the patience for that. So that's kind of my which is kind of nice, because it kind of pushes you in a certain direction.
The usability trade-off.
Exactly. You need to make trade-offs, and it gives you some interesting discussions, I think.
It's the plague of AI that we're surrounded by. I do need to ask the question, is there any quote unquote, it's a terrible use of the word, but learning component to how you've done this? Or is it basically every time you're starting from scratch with this image and this image only? Or is there some onboard kind of terrible use of the word knowledge that's been built in by sampling lots of images?
No, there's no, it always gets all the information from the images that is presented to it. So, and I think this is one of the ways in which it's different from, let's say, you see a lot of color AI and all these other websites that do kind of similar things. From what I can understand, they have obviously trained an AI algorithm to kind of you need they essentially trained, probably use a large number of grades to train the algorithm to do what it does. And in this case, I try to go back to kind of first principle models, which just base themselves on, they don't need any kind of training, or it's all in the assumptions and in the way that it looks at a picture, which is going to give you the result.
Right. Interesting. Yeah, I mean, I think these learning systems have, in a creative industry, have serious problems, because you're zeroing in on exactly what, like if your creative brief changes, you don't want to be zeroing in on some other previous creative brief. Sometimes you want to break the rules as much as you want to, the conventions that you want to stick to, sure, but we're in a creative industry, we want to break the rules quite often as well. Just looking to the future of it, I mean, could you see a way, I mean, I think you've already mentioned it, could you see a way that you don't just walk away with a 3D LUT, you walk away with something that's parameterized and almost like, I don't know, just to put it in a non-technical way, if you could say that you could take a LUT, 3D LUT, and you could reanalyze it into some sort of vector LUT, which could have Bezier controls that you could give back to the person to tweak further.
Yeah, so I think one of the we've talked to a couple of colorists over the last couple of months, and one of the elements that came back a lot was maybe I don't want an exact match. I want to get it in a certain direction, but I want more creative input on how much of for example, this I want to use, and how much of that, and I may want to keep. And so this is kind of where I think the future is going. So in one way, it's essentially the model does color matching, but it can also kind of give you an idea. So the way the image was manipulated, you might say. So it gives you a sense from a certain perspective, obviously, which is a distribution perspective. It is a way of representing a grade, and in some cases it might not be a perfect representation of that, but I think it can be useful. So this will be kind of the challenge. So what way can we use the result that are in the LUT to kind of inform essentially, and kind of give more tools to say, okay, if I want to change this in this direction, I have to use this tool, or if I want to use this direction, I have to use that tool.
Right.
So yeah, that's I think is a big question. So how can you make it more creative? Because it's obviously most people don't want the exact same thing. They want something that's creative enough and something of their own. And at the same time, yeah, you want to be able to kind of analyze, to use it more as an analysis tool to analyze a picture and see, okay, how was this achieved? Okay, and learn from it and then apply it essentially, rather than just trying to copy paste essentially in a sense.
Yeah, I mean, what has come to me just through the process of actually using the tool, I've realized that whether this is what we do always with matching or creating looks, it's almost like you can use this tool to be like a gravity to draw your pixels towards a certain thing. It doesn't, and like you say, it doesn't have to be exact, but you can use that as a steering function to get. I definitely don't want anything in these these two edges, but I would like my stuff to center and warp in a certain way. So yeah, I think this is a very, you could say it's abstracted, but it's also, it's like microscopic analysis, but it's also an abstracted view of like, okay, I'm stepping away from, is it contrast? Is it, brightener? You're stepping away from the exact tools that we used. You're going to a global view, but you're actually doing, you're analyzing the chemistry of the pixels in some weird way. I think this is very fascinating.
Yeah, and there's another element, and this is kind of where we got, well, in the first discussions I had with Troy were a little bit about this, where, so how do you, if I have two images which are not the same, how do you define brightness of the image? The algorithm has to interpret it in a way which, at least to our eyes, the two images will look like they were shot under the same brightness, or they fit in the same kind of family of looks. And this is kind of a weird thing, because if you look at the image itself, if the image has a different composition, it will by definition have a different distribution of likeness in it, because some areas will be darker, and if I average over it, that average is not going to represent the way our eyes perceive the brightness of the image. So this is an interesting discussion, and I think the algorithm kind of inherently comes up with a definition for this, and depending on, well, if it's a good definition, the images will look similar in terms of their brightness, even though one shot might be a close-up, for example, of the one that you're showing now, the two girls in the car. So visually, I would say, aside from all I had a lot of discussion about the cognition of the red in the guy that's sitting there, and how our eyes perceive it and how realistic that is. But just from a distance, you can kind of see that, okay, I can at least see that these two things could be viewed as having been under similar conditions if you compare them. So, and then the question becomes, is why is that? So why do our eyes interpret two pictures, one of two girls sitting in a car with some bright backlight, and another picture as being visually similar? What is that, essentially? Given the fact that they have completely different content, the composition of the image is completely different. And that, I think, is just in of itself a fascinating question. So how do we do that? How does our brain and how do you capture that in terms of some relatively simple mathematics? That's another yellow dog.
Yeah, that's the $1 million question. Yeah, I mean, I'm intentionally skirting around the visual cognition stuff. I mean, we've mentioned it several times. Let's not dive into it just yet, because I know it's a bit of it. But yeah, okay. So generally speaking, the mathematics that we're generally using here it's a lot of calculus, differential equations. We're working about rates of change. Is there any statistical analysis? Yes, it's statistical analysis, and also gradients, and that kind of thing. So that's quite a. I mean, would you consider that as one domain, or does that feel like we're actually bridging a lot of different domains to achieve this task?
I think we're bridging a lot of different domains, because like I said, we look at a picture, and there's some kind of abstraction of the picture happening as we look at it, so to speak, because we don't view the picture we don't view any picture in exact terms. So there's a level of abstraction which makes it such that an image can be very different, but still represent a similar look, essentially. And I think that's where, we start manipulating all kinds of things to kind of achieve that. But essentially, that is in effect, like I said, when I talk about P style for me in the theoretical terms is kind of the absolute. It's kind of the same question with color balancing. I had a discussion which is kind of related to this. So what does a balanced image represent exactly? So why do we look at an image and say, okay, this whole image is yellow shifted? Because it's not just a simple, let's say, straight line. I just remove some yellow, and there's something more complex going on in terms of where we interpret all the relations between the colors, and that's even outside of the whole realm of visual cognition, like we said. But it's also to do with how do we view these colors relatively. And in an algorithmic sense, this also happens essentially, but it's not just relatively within the picture. It's relatively in terms of a higher order distribution, which is what I call P style.
Mm.
This is kind of the difficulty, I think, because in a way you're trying to convince to show to people this algorithm is good at color matching, but at the same time you're trying to have a more separate discussion. So even if it's not perfect in every sense, do the theoretical concepts behind it make sense, even if in some cases it's too simplified, or we've thrown away too much essentials, which might be a cognition effect or whatever. Does it represent? Is it a reasonable representation of what we try to do when we grade a film? So what is the process? So how do we look at an image and the manipulations that we apply to it?
As filmmakers, we obviously look back to what we would consider the source and say, okay, camera has camera space. I graded it as 709. I did this. I put, these specific transforms. So we would always look back at what are the tools to try and interpret, this whole thing. But there is a sense where you're just looking at the final result and saying more or less, closer and further, and in distributions. Now, just to lay more of the foundation. I mean, we're going forward and backwards in lots of different directions here, but the concept of entropy, which is quite interesting. So, okay, first, what is entropy and how does it apply to an image?
Well, entropy is kind of strongly related to the number of states, you might say, that a system has.
Right.
The more states it has, the higher its entropy, essentially. So it's often related to configurations. Many configurations means high entropy. Limited configurations is low entropy. And in this case, if you look at the image, the way I've used it is to kind of define the image complexity, because essentially a grayscale image has very low entropy, because all the colors are essentially on one curve, which goes from black to white, and that's the only and then the amount of how much gray of which tone is in there is the only variable that you have. If you then go to a two-color system, which is obviously what we had when the Technicolor people invented these processes to kind of use the red and green to approximate reality. And it's kind of interesting because what they did is something that we now try to go back to it and kind of see how does this work. If you try to represent something in less colors, a lot of people have kind of tried to reconstruct this Technicolor, I think two process that they use.
Two-strip,
and also the Technicolor 3 process, of course. So in understanding how does this work, if you go to two colors, you have more entropy because you have more, obviously, much more space to manipulate, but it's a surface in 3D space essentially that you're manipulating. And then you go to 3D, you have even more configurations that you can use. So that's essentially how I look at entropy. And the algorithm itself generally needs a reasonable amount of entropy to kind of, especially if you go to the model which no longer needs composition, because composition kind of helps you to anchor the whole image. But once you decouple it from its composition, it has to get the information from somewhere, and the way it does this, it uses all the different variations in color and compares it to the variations in color in the target, and kind of extracts these relations from this. And the less entropy it has, the less kind of information it has to work with to figure out how these relations are formed, essentially. So that's the way I use entropy, in the sense that this became especially apparent if I went to the universal model, because there you make the most assumptions, so you need the most information effectively to get good estimates of these distributions. So there I quickly found if the entropy of the image is too low, meaning that it's a very low saturation image with where essentially everything's kind of pushed towards a very tight distribution, it becomes much more complex, especially if you want to go This was another rule. So it's easy to go from many colors to few colors, essentially, which means you're lowering the entropy. But increasing the entropy is a lot more difficult because you're trying to essentially take a very tight distribution and have a very kind of make it have it expand. And this is a much less precise process to do. And this is essentially why I think color restoration is such a challenge, because fading kind of reduces the entropy of the image till it's essentially a monochrome image, and then it fades kind of to to oblivion.
We're trying to expand it back out. I mean, this concept of entropy is quite interesting because I did my duty and I went to the Wikipedia page and it gave some interesting examples. Like you put the milk into the coffee and they're separate things, but over time it turns to this just coffee colored thing, the milk. And there's no way to just bring them apart. Or you burn a piece of wood, you can't unburn the piece of wood. It kind of goes to this equilibrium state. I mean, and then I thought, okay, but an image, it's not like water falls down when we drop it, or, it falls down a waterfall, it doesn't fall up a waterfall. There's no gravity that's pulling the images. But then I thought, actually, there is. It's the creative choice. The entropy is the creative choice. It's saying the image looks bad if it's that bright or that dark or that blue or that green. There's this kind of creative choice is now the gravity which is pulling the image into its place. But I did the extra step of taking a random noise image through the thing, and that was like 0.9 entropy, and then like a flat gray thing, and that was like 0 entropy. So I just had to do that to understand what your entropy terms were.
Well, it's interesting because essentially the burning of the wood kind of represents the, for example, the black rush. You've kind of destroyed or removed any possibility of kind of retrieving the original state of the image, and obviously the whole lock image idea is to try to be able to manipulate the image without losing entropy effectively, because you want to be able to kind of reverse that process. And once once you effectively permanently lower the entropy of an image, it becomes very difficult to kind of increase it again to a more complex state. So I view it kind of as a form of compression. So you might say that color grading is a kind of creative form of compression, where you try to compress the image into a certain subset of where it could possibly be, which represents a very unique look, but it's compressed, and it's a creative use of removing things. It's often more about removing things than adding things to an image, because
I totally agree. I mean, especially in the case of where LUTs are used for calibrating monitors, the rule is that the native space has to be larger than the target space, because the LUT can only reduce. Sure, I mean, a LUT theoretically can take pixels and move them to bigger stimuli values, greater stimuli values, but to some limit. So you've got this broader maximum that you're always trimming down off. And mostly that's what we're doing when we grade, exactly as you said.
Yeah, and the interesting thing is, if you look at color restoration, for example, we know that you cannot kind of get back the original state. You can obviously improve the image to make it look colorful, but the price is, for example, more color noise and all this kind of stuff, which is the consequence of having lost information effectively due to the fading process. And I think it's kind of the same thing. Yeah, I can transfer back something from 709 to HDR color space, but I'm never going to get back those highlights. They're just lost due to the transformation. And I can hopefully, with all kinds of tricks, make it look better than it did.
Right. The way that, taking a 2-strip, this full color image and taking a 2-strip and then limiting it down to one, like you say, the plane. Yeah, I thought those were very, very fascinating. Just to pivot slightly, I mean, it's something that I think you've encountered slightly on the forums already. There's this obviously it's in all areas, but all industries, but especially in the film industry and in terms of color and coding for color and ingenuity and all these interesting products and tools that are coming out. There's this discrepancy between open and closed source, developing software, and is it a creative collaboration or is it the property of a person or a company? I mean, What are your insights so far? In some sense, it's a black box, and we can't see what's inside. And obviously, your company needs to protect. It's a product that you want to go take to market and to sell. But how do you see the benefits of these two different approaches, and how do you see it playing out?
So it's kind of always kind of I think a process. You don't always know if things are going to be open or closed source essentially, because in some cases it's actually beneficial to open up the source, even though others can obviously copy it. Then,
Right.
if you have kind of enough of a head start, you might say, it can be beneficial to just decide. So for us, it's not. I don't think it's necessarily that we always want to say, okay, I'm not never going to say how this works. Obviously, there are some specific mathematical tricks that you can use where you say, okay, that's so this is why I kind of on the forum I said, okay, how am I going to do this? I want to, I don't want it to be a complete black box. I want to because I think the theoretical concepts are interesting, even though the specific way I implemented it is then closed source, you might say. I think that the concepts are what drives the whole idea basically,
Right.
and then the question is, yeah. So at some point, do you write it down and publish it? Because and at the same time, it might have some use in different ways, or do you keep it? Yeah, that's kind of. I think it's always a difficult question in a sense, because I think in some ways we tend to be too protective often of know-how, thinking that know-how in of itself is where the value lies. And I think the value ultimately lies more in the cooperation that you have with different people, in the continued kind of research funnel, the discussions around it, and being able to kind of transform people's ideas into concepts and algorithms, and trying to protect a very specific algorithm from getting out or
Yeah.
so I'm kind of on the fence a bit about it in a sense. So I kept it closed source to an extent because I really didn't know where this was going to go. But there's also kind of this part of me that said, okay, maybe I should just write it down.
Yeah, well, I think once it gets into other people's hands, whether they're looking into the code or not, they will use it in surprising ways, and I think that is the evolution of the product. Whether it's
Yeah,
open or closed source, it'll definitely evolve into very different things, because it's got this chemical distribution nature to it. I think it's going to have lots of other, it could do microscopic changes on the image that you're unaware of, like grain. It might have interesting implications for that. For noise reduction, it also might have it might be a better way to do noise reduction. Yeah, I think there's a lot of room for that. But yeah, I mean, I think maybe you're safer for the people that are directly in the industry, in that um, there's a degree of maybe the access to Matlab and the how it works within Matlab that might be a bit more limited. So yeah, I mean, it's an interesting debate, and I'm very, I'd say, happy to hear that you kind of you see it for what it is, because yeah, my experience is that the collaboration always leads to better things.
we tend to over say value protectionism in knowledge and underestimate the way cooperations with people is what drives
Yeah,
innovation and what drives ultimately successful products, and not specific know-how. That's always going to be limited until a very short time until somebody else thinks something similar, and then you have competition. It's an old style, I think, of doing things, to kind of put everything in patterns, and yeah, I don't think it's a way that's the future, especially in this new chat GPT driven
yeah,
AI economy. I think the strength is going to come from, like, kind of like in the internet, from many connections. It's the connections, and it's the know-how, the way you can kind of very quickly come together, define a problem, and then find a solution for it by combining know-how from different areas of expertise. That's, I think, where the future lies, and not in these kind of, how to say, very isolationist
yeah.
approaches to research and know-how.
Or maybe it's something like you have the architecture and the more complex thing, and then I have a module, a version of it that I can feed into your thing. But it's still your thing. You're still in control of it. But I can do flavors. I can do different takes on it. This collaboration is obviously going to be linked to what it means to be a colorist, the day-to-day, and what I need it for. So, I mean, I think it's roughly three, if I break it down into three things. The one is, let's say, the Instagram filter type of usage. So I've got an image, it's a still image. This is more applicable to stills, I think, than to video, but I just want it to look like sepia, or I just want it, and it's already a formed image, and I'd like to do a style transform. And I think that in that sense, the product is very well formed. And because in that sense, you're not comparing, there's no actual right and wrong. It's just how much of this effect would you like? And in that sense, I think it's very strong. The second sense, which would be, I've got all these scenes, these shots with one scene that have to look exactly the same, and they were shot by different cameras, different angles, like a drone, and then the wide and the tight. I've got to match all of these. I think in that area, it's going to be, sometimes easier, sometimes harder. So that is the one requirement that a professional colorist would definitely need. And then the third is to be as a higher level, I wouldn't say look scraping tool, but at a crude level, it is that. But it's more just what we're talking about now, this getting into this level of the highest level, which would be this concept of distribution and applying gravities to your signal. I want it to be, move me into this kind of area and less into that kind of area. I think that's going to be the areas of it. So yeah, I mean, I think there's lots of, that could be a layer that has to come in now is the how I need to pull it into my current pipeline and what I'm missing, and that could be the next layer of development. I've had 30 years at doing this, and probably the one thing that is really the bugbear is conforming. We have an offline editor that does a cut with low res footage, and we've got to link back to the high res raw files. So if there's any tool that the industry really needs, it's a automated conforming process. But the next one probably is matching. I'd say that, the bugbear, the boring part of the job is to say, okay, I've done the creative part, I've built a lovely look, but how do I propagate it through these 1,000 shots? So in terms of solving a need, it really does resonate. Yeah, so I mean, I'd say that's an encouragement. I mean, in terms of developing a product and how it's marketed, I'd say that the question then is how it's integrated, how closely it sits inside that. I mean, have you had thoughts about that? Is it could it be an OFX that sits inside a color correction software?
Yeah. So originally the idea was, so can we get it in a software program like Resolve, for example, in a way that's easy to kind of use it as a building block in between all kinds of other operators. But ultimately, whatever complexity is behind the algorithm, it's a tool. It's kind of like for me, it's kind of similar to I can use a handsaw or I can use an electric saw.
Right.
It's going to have advantages. There's also going to be some things that you have to keep in mind when using it, for example, because often what you see is that the first thing people do is they get the algorithm. Well, let's find the most weird combination of images and match them together. And they often assume, I think that's kind of also a thing, and this is not just for this specific algorithm, but this is something that we encounter in our daily work kind of as data scientists, is that people often assume models are, it's a push of a button and it's going to give perfect results, when in fact it's just it's often just as difficult, except you have to look at different kind of parameters. So it's a different way of looking at the same problem, and it can help you in certain directions, and it's obviously good at some tasks, specific tasks, but it's not going to be a one solution fits all kind of magic button that's going to automatically do everything for you, for example. So I think that's kind of the way I look at it. It's a tool. We have to kind of look. So when we started discussing this, because Colin Kelly contacted us at some point through this forum, and then the question was, so how are we going to do this? Because from one side, it's, does the algorithm do what it's supposed to, essentially, in the sense that if I feed an image to it, does it give an acceptable result? Under what conditions are the results good? Under what conditions are the results not so good? And the second question is, okay, given that it performs under specific constraints, how am I going to kind of put it in the workflow of people? And our idea was, yes, we want to go towards a situation where it's a plugin in Resolve, or in the case of we also had photographers who express some interest in Photoshop. So this would be the kind of the dream situation where you, obviously we're a small company, so we're not going to just spend huge amount of money to kind of build a whole lot of software. So we kind of need to think about this and see who's going to be the first group of people that we want to. And this is kind of always, this is what we did with the the drug analyzer. So the first thing we did is contact people that know what they're doing, essentially.
Right.
We're not forensic scientists, we're data scientists. So get in contact with forensic scientists, get in contact with the police force, and let them tell you what ways they would see, what opportunities they would see for such a product, and then develop in that direction, essentially. And this is kind of what we try to do here. So I'm not a colorist. I don't have the eye for it. I don't have so I can see certain things, obviously, that are very obvious. But so let's kind of set up this cooperation with colorists to see where are the opportunities and what should a product look like if it's going to be useful, because ultimately that's what it's not about the algorithm, it's about what kind of problem can we solve, or what kind of value can you add to someone's work process, in the sense that can I make it more efficient? Can I make it such that you have to spend less time on tedious tasks and more time working creatively, essentially? These are the kind of things where I would envision, and then how would it fit then? How would the product then have to look to align with those goals, essentially? And then we're kind of still in the process of finding that out, essentially.
Yeah, I mean, because I think in some sense, definitely the higher level usage of this tool is offline. You know what I mean? Like if online and real time and doing the grade is what we call our online process, our grading and online process, it's actually a step back. It's a pause from that, or it's before you actually start your grading, or you know, it's some pause in between where you say, I'd like an interface where I can have a media pool of images. I can build a composite of source images that I'd like to, you know, be what I'd like to adjust. My target images I generally like to work towards, and then the LUT manipulation processes, and also maybe ways to directly feed that LUT into where it needs to be. So for my color corrector, also LUT manipulation tools like smoothing, view of the 3 1D curves, as well as the LUT itself, etc., etc. So yeah, in some sense, it does actually, like the in-depth use is actually outside, but there could be a quick and nasty version, which actually is, you know, just press one button and it fixes all, or supposedly fixes all. But you have to have this process of what do you reference to. I think that kind of breaks the logic of the possibly in Fusion, where it's more like, okay, this is an effects process. So now I'm saying I've got two inputs into this thing, and it gives me an
well, I think ideally you would want it to interact. So if you're going to use inline, then you would want to kind of use it more as an analysis tool, which gives you a lot of a kind of 3D space in which you can manipulate stuff, so to speak. So where you can say, okay, this is kind of the way the image would look if I were to go for this. But now I want to kind of interactively adjust it. I want to adjust this axis, and I want to adjust this axis more than this direction, etc. You kind of give a kind of starting point, but then shape it kind of like the person kind of how's it going? What's the word? The one that makes the statues.
Sculptor. Yeah.
Yeah, sculptor. Exactly. To sculpt it in the direction that you. So it only gives you a kind of rough starting point, but then it should give you the opportunity to kind of manipulate that in ways that are interactive. Kind of like I always kind of envision this idea. You know, if you ever saw the movie Minority Report.
Yeah.
Where they're kind of grabbing all kinds of stuff, shift this way, and have a kind of very interactive way of turning the distribution, adjust it, see how it affects the image. Now I want to go back to the previous thing, etc. So to have a more almost like virtual reality way of looking at an image from all different sides.
Yeah, well, I've been harping on this. I'm hoping someone will just go ahead and design it. I think forget about a manipulation tool. Obviously, that would be great as well, but just a visualization tool of the current signal as it is, to be able to basically spin it in front of you and look at it in some kind of VR process would be really amazing. And then if you can go and do tweaks based on that. So yeah, I mean, I really do think it does have legs. Yeah, I mean, just an aside point is that as someone who's been doing it for a long time, the actual process of matching, obviously you can choose different tools. You can use linear gain, you can use lift gamma gain, you can do all sorts of things, but it's sometimes something that you can't actually explain what you're doing. It's very instinctive. So your hand, it's a very much a live hand-eye feedback thing. You like the more or less hot cold moving it to the right place is actually, it's hard to explain. So it's actually very hard to teach because you know how to do it, but you don't know how to explain it. The other issue that we're facing is that historically we've never had the right tools. We grew out of lift gamma gain was out of the telecine era. We had lift gamma gain, which was essentially a great way to, within your 1 volt range that the signal could sit in, to stretch to the top, stretch to the bottom, and do balance between, and that was it. It had nothing to do with linear exposure, the way light was captured, all these various log and linear and all these good things. So yeah, I mean, in a sense, this is really interesting because it's a totally new approach to how you could stretch and manipulate the signal, just with the other component of how do you interact with it. That can be the hard part. It's great on the analysis, data analysis, but how do you, what do you do next with the results?
Yeah, I think
It's the black box issue.
no, exactly. So that's a really good question. So one way is to say, okay, how can you learn something from these distributions essentially that will make you that will come to different tools. So okay, we need different kind of settings to manipulate effectively, or you want kind of more a dynamic way of doing that. So essentially, you still have the same three buttons, but they represent something different depending on how you rotate the image or how you to kind of give you more leeway in the way you can manipulate the image based on and get kind of a visual feedback. So this is kind of, I think, an interesting thing to, and this is typically something I think that you can only kind of develop in cooperation with, because it will require in-depth knowledge about the way a colorist looks at an image, looks at the data essentially, and how that translates to the image. But this, like I said, this can be a kind of a good starting point for discussion. Essentially, I think that's aside from whatever utility it has as it is.
Yeah, I mean the stepping stones that I see, it's kind of, we had 3x3 matrices. They were very crude and then people have developed essentially 6x3 matrices, and then tetrahedral matrices, which can essentially pull the cube becomes triangulated slices, which you can move. And now this is you defining axes based on the signal itself, not based on some preset axes, which is really exciting.
Yeah.
You may think this has got nothing to do with you, but this is an interesting tangent I'd like to go on, and let's go on and see where it leads us. So let me just I'm going to put my Luddite hat on and ask, why do we need, okay, firstly, is this a kind of automation? I think, yes, it is. It's kind of a matching, automating the process, the boring process of matching a whole lot of shots. Do we need this automation? I mean, I think the answer is yes. There's more content, more demand, and I don't think that's the issue that I'm quite. Let me give you a bit of background. I've heard that people in the music industry, they feel that music is all essentially the same now. It's a different song, it's got different words, but there's this underbelly of sameness. Like it's always auto-tune on the voice, it's always this, it's the same samples. Is that a danger in a creative industry where we've already shot this theory in the foot, because we've already spoke about all different great applications. But let's say we're using it on the crude level of, I just want this to match that. Is it a bad thing for the creative industry that we're narrowing down we're just narrowing down variability?
I think so. I think the how should I say the idea, like I said, in the music industry, where you kind of get everything is kind of pushed through a pipe and it all comes out like blended together into one mush of sameness. I recognize that as in a sense, and I think there's a risk, obviously, that if you're going to rely more and more on automation in color grading, that everything is going to kind of, to a degree, you see this happening already, and that's nothing to do with automation, but it's to do with You can see that there are different eras. There was an era where all films looked very bright and colorful. Now we're kind of in an era where everything looks kind of desaturated, and so we already tend to kind of
trends and yeah.
There are trends, but also people tend to move with the trend essentially, and it often takes someone with a creative vision to kind of break that trend and do something which is different. And you see that especially the industry is going to, I want it to look like everything else looks. So it needs that today desaturated stuff is popular. So make it look like whereas in reality, what you obviously want is something that, and that is, I think this is generally a danger. So for example, I've often asked myself, why in God's name do we need a Star Wars 7, another Lord of the Rings movie, etc. So there is such a paradox in a sense that
right.
What we want essentially is the same feeling we had when you first saw Star Wars, when you first saw the Lord of the Rings, that kind of feeling of amazement. And we think we're going to get it by copying that, which is essentially, and we already know inherently that that's not going to give that same high. What's going to give that same high is something truly newly creative that's going to be different from the thing that we looked at.
Yeah.
But it's really interesting that we always go towards repeating the past in hopes of reliving something where you know that every time you do it, it's going to, there's this law of what's it called?
Minimizing returns, yeah.
Exactly.
The business end of it is all, people want to milk that cow again and again and again. But yeah, actually viewers want something that's beautiful and creative. Like in Asia, everyone now aspires to this version of beauty or these standards that Korea, everyone's chasing, like thinks Korea is, movies and, beautiful women, handsome men. That's everyone's, gravitating towards that. So basically your product needs the anti.
Yeah.
Sure, you can pull in towards a thing or you can bounce away from a thing.
No, it's interesting. We are kind of working. My colleague is really busy with a book about business strategy, and one of the things this guy says is you don't need to be the same. You need uniqueness to. You're not going to be successful by copying somebody else's success. Success is in creating something new, something unique, obviously of value. I mean, not everything that's new is obviously going to be valuable, but
right.
There's an important element to that. And I kind of view it like, let's say you might kind of say that Star Wars 9 or Star Wars 25 in the future, she feels like copying an old VHS tape, where it's very obvious. Every time you copy it, it still has it becomes worse essentially.
Yeah.
And there's this really weird dynamic also in fan bases, where being too different becomes kind of sacrilegious, you might say, because
right.
We want the sameness, but we also want it to be different, and you kind of have to balance these two things. But if you make it too different, people are going to say, "Oh, that's not Lord of the Rings, or that's not Star Wars." And if you make it too the same, it's going to feel like some kind of pale copy of what's done in the past. And I think that's but ultimately, I think the real thing is, and I think the real strength of periods like the 50s, the 60s, the 70s. Is just these very innovative filmmakers that really put their stamp on something and made something that did not exist. And I think, it would be. I think our industries are just too focused on wanting, let's say, security, wanting to be sure that something is going to make money,
right.
rather than trusting in filmmakers to create something truly special. And obviously, maybe a lot of these things are going to fail, but that was the old business of making film.
Right.
The one smash hit every year, and that finances the rest of the.
Right.
I think that's kind of what also happens in the music industry. People are trying to estimate what do people want to hear, whereas the real magic is in. What don't people know they want to hear? Essentially, that's
exactly, yeah. Surprise them. It's the detriment of these data-driven businesses, right? Analytics-driven businesses rather than just free inspiration and essentially humanity-driven businesses.
Yeah.
Yeah. I mean, just what slightly closer to the actual practicality of matching, making all the shots match exactly. Sterilizes the thing and takes out some of the randomness, some of the beauty. And so I'd say that a job that is really, 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 really well matched is close to like a corporate video or a commercial. That's what I expect for those kind of things. Slick, like a bit too slick. but a gritty film, a true story, some kind of really moving humanist kind of story doesn't have to be exactly the same. It's almost like every image must be beautiful for itself. So yeah, I mean, these are all challenges of the filmmaker.
There's beauty in imperfection, you might say. That's all
Yep.
also, I think, in a sense, what drives the whole debate of which are better, the original theoretical version of Star Wars or the special editions.
Right.
People fell in love with the imperfections of it, so to speak. And the same thing, I read an interesting video once where somebody said, so what makes film look so much better than digital to many people? And I thought one of the interesting elements yet it was not the grain that is the thing, but the fact that when something is shot on film, the image is never still. A perfect digital image which is frozen and doesn't move. Film is always moving, so not even the grain, but also the image itself is weaving in a way, and this just gives it a lively effect. So, and he had this very simple thing where he said, "Oh, I'm just going to add a little gate weave, a little bit of." And this completely livens up the image, even though it's digital, it has no grain yet, but even that simple thing, add imperfection to it to make it look better to our eyes, essentially. This is an interesting concept.
Yeah, well, I mean, you can spend a lot of money sterilizing out all that stuff, and sure, it's cleaner, it's 8K instead of 4K, it's all these things, but yeah, you end up sterilizing the beauty out of it. I mean, just on the topic of restoration, which I think is possibly one of the main markets for this product once it's out there. I've recently done a restoration of it's a 20-year-old film, and it was, a kind of an epic film, like a martial arts movie in China, and it was very much about color and very extravagant art direction. Shot on film, so the neg was all rescanned, and it had all been stored in different places, so it all aged differently. There was lots of visual effects, and that was the year 2000 DI visual effects process, so the color management was terrible. The resolution was also different. All the effects shots have got this weird green tint on them. The color space was essentially totally different. And also massive scenes with thousands of actors shot over weeks and weeks, morning, noon, and night. So, it's the toughest job I've ever done. And this could have really helped. This becomes a rights issue. But if somehow I could get that footage to you, or the production company would release that footage to you, and that could be a sample set that you could work on, I think that would be amazing. So I mean, I think that, if someone hears this and has some idea of some archive that's out of copyright or something that you could work on to firstly refine the tool, but also, I mean, I don't know if you've got any avenues.
I tried. I did an example on one of the. It was actually a government-funded project where they restored these old government films from, let's say, airmen from the 50s and 60s that were shot.
Right.
And these films had all faded pretty much to a kind of purplish color. There was some color left in it. And then they put it on and they said, well, this is kind of the best for you. They kind of balanced it a bit, but it didn't have any color anymore. And then I saw, okay, this tool can be really useful because if there's color in there, it can reasonably get it out, so to speak. And I got a lot more color from it. So that was the. But I contacted the guys, but I didn't respond. So that was it. But these kind of films would be kind of cool to work on because essentially, if you have a good scan with a good color depth, I think there's a lot more that can be done, especially on old faded films that look like they're practically monochrome.
Right.
Often there's still enough of information in there to kind of make it look. And then obviously you have to think about, okay, I don't want it to artifact, so you need a lot of smoothing in there and all kinds of operations to kind of, I think these would be kind of really interesting test cases, so to speak, to see how far can you go with it. So what can you do with, for example, I saw one, Robert Harris discussed the way the state of the movie The Alamo, which had kind of completely faded away.
Mm-hmm.
And if you really were to have a really good scan of that film, is there still color information in there that can be retrieved with an algorithm like this, so to speak, essentially, which can take a reference shot from a different film, because that's obviously the problem with old films that are completely faded away and you don't have any kind of reference to it.
Yeah.
How can you restore that color, so to speak, in a way that is controlled and it would just be really interesting to kind of delve into that and see what can be done.
Yeah, I mean, I do have contacts to the film archive here in Taiwan, and they basically restore like about 10 films a year, and they've they've got hundreds of films which they gradually need to work to. So yeah, I mean, I definitely propose this to them if they're willing to put up a project, and then we can work out some collaboration. I think this is really interesting.
Yeah, it would just be interesting to see what can be done. Can you kind of get further than what you could traditionally be able to do? And that's kind of another question from all whatever commercial stuff or whatever. It's just an interesting project to consider. So what's possible given the current state of technology, and what can you do to kind of restore color to something which seems to have none anymore.
Yeah, I mean, in terms of the team, that's traditionally it was always just the colorist go do it, and you just did what you had lift gamma gain, and you just worked and did the best you could. Now there's this color scientist which come into the tool, but this is almost like another level of abstraction. It's like a data analysis which is even further abstracted, which could lead to a whole lot more insights.
Now I can show you a few examples, kind of going from the different types of models.
It would be great.
Well, this was essentially the beginning, so to speak. So these kind of scans, red faded, high resolution. I mean, it was a 4K image. So the idea was back then, import a target. So this one, for example. And in the original algorithm, this already was a bit of a challenge because you assume that the content is exactly the same. You have to make sure that the image is cropped in the same way. So that would inherently already be a challenge, because once people started using the tool, they didn't realize this, and then they got bad results because they were directly matching these two images, and things were being manipulated because effectively the cropping changes the composition of the image effectively. So that's
right.
We now build a model. So this was the first kind of application of this algorithm in a sense. So here I used the scene match model because I don't want to have to crop the image. So it essentially takes this image and then it matches the colors of the image, effectively restoring the color for something like this, so to speak. So this is essentially what it was originally developed for doing.
Yeah, and this is very impressive.
So and it's really fast. So for example, this would be in terms of restoration. And the good thing is that in this case, I obviously used the target was the same image, but from a DVD. But you could find any image that has kind of a similar feel to it online and use that as the target, and you would get a similar result. So because the algorithm doesn't look specifically at, like I said, the fact that it's Carrie Fisher standing here. It just needs an image with similar grayish bluish background, a girl or a man with similar skin tones, and it will, based on distributions, kind of figure out what should happen with the image.
And then you've got a LUT there.
Yeah, exactly. So that I can visualize the LUT as well. You can rotate it. This is part of the image, so you can kind of see the way the image is manipulated, and it's actually not that there's some shifts towards, obviously it's red shifted, so it's going to shift it in the other direction.
Right.
But this is not actually that. I've seen LUTs that look a lot more exotic, I would say.
Yeah, this is very smooth.
Yeah, it's smooth, and it's also kind of still pretty cubic. There's some shifts here, so you see here the fact that the red it's kind of shifted towards the green direction. And what this image does is it plots the original colors as they were in the space that they're going to occupy. So this red color has moved towards
cyan, basically. Yeah.
Yeah, exactly. So there's less red in it. It goes from from 1 to about 0.8, etc. So in all these points, this is part of the algorithm's design, is that all these operations should be smooth. All of this should be smooth gradients. Anytime I have a non-smooth gradient, it's going to create artifacts essentially in the image, which is what the first version when you use histogram matching directly is going to be problematic, because it's going to place all these, it's going to match too exactly, you might say, in terms of the histogram, and this is not what you want, because there are always tiny variations which cause to be slightly different, and you don't want it to kind of be overly focused on the details, you might say.
Yeah, you'd end up tearing the image, sure.
Yeah, and this was another image which is interesting, which I wanted to show, which is the way the algorithm kind of works. So this was, I did an example online of where I matched the movie Joker to another movie, and Joker obviously had and this was a train scene, which is very, very heavily green tinted, which is on the left. So you see kind of the colors in the image, which is a kind of green color. I used, I think, a frame from the movie Fight Club to kind of match it to. which is more balanced, a little bit more contrasty. And you kind of see here how the algorithm manipulates the distribution. So it starts off with this green distribution, then it over many iterations kind of tries to fit the same shape that it has in the target frame. So it's a little bit more shifted, it's bent, whereas and the bending causes the kind of grade effect, which has but it is more green and less green in other areas. And then you see that over time it kind of slowly manipulates the distribution to fit the intended distribution, you might say.
Right.
This is the example of the Technicolor 2 process. We start obviously with the original image, which I think the movie
Were things.
Yeah, exactly. So I think the movie already trying to go for a kind of Technicolor 3 strip look, a very heavy saturated look with a lot of contrast in it. Yeah, which was the image I took. I think there's this really nice color history website where they have all these old scans of films all the way going back to the 1920s and all these different processes. And this was actually a really good looking Technicolor 2 print. Often they look kind of a bit off in the sense that, and this one had really nice saturated colors with nice skin tones, even though it's only in 2-color. Often the skin tone tend to look a little bit reddish, the 2-color system, but I think this one actually has some really nice skin tones. I think of a universal match. And in this case, it's not full color, so it's a bichrome system. So I have a bichrome option in the model.
Right. And
this kind of means, and I'll show that in a moment, it's just going to assume that all the colors are supposed to be on the surface to kind of force the model to go into a 2-color system. So I'm going to build the model. And it's kind of interesting to look at the LUT for this because there are some, let's say, useful effects there to analyze.
As an analysis tool, it gives a lot of insight.
So you get this result. So yeah, you start off with the original. These are the type of colors that you want, and you get something which looks very similar in terms, at least, of the color tones, similar skin tones. And the interesting thing about this, obviously, is that the LUT is going to be effectively 2D, but it's not going to be exactly. So one of the things that I discovered very quickly when I implemented this is that one of the effects, for example, of going from one color space to the other is that no color exactly fits in one space will exactly be on the surface in another color space. It will be approximately, so the surface might be bent a little bit in space.
Right.
So this was one of the elements that I had to include. So yes, put it on the surface, but allow some bending, for example. And what we call monochrome often is not exactly monochrome. But there was this really nice image of somebody who had graded a girl against a uniform background. The entire image was kind of greenish brown. In the shadows, it was a more reddish color. And in the highlights, it was more yellow, but visually it looked monochrome. But this kind of means that the LUT is not going to be a perfect straight line in space. It's going to be a bent line, which starts in the reddish area and starts to move up towards the yellow. So you get this kind of really kind of shifted cigar shape in space. So,
right.
So and this was a really interesting effect that I didn't really consider when I first thought, okay, we're going to do a one-color system or a two-color system. Everything is just going to be on a nice straight line going through the origin.
Yeah, it's got to sit within a three-dimensional color space. So yeah, all of these more subtle transforms are possible. I did a bit of a weird one. I took an image and I matched it to black and white random noise, and it had this. It did a similar thing. It was pretty much one-dimensional, but it had this, magenta in the blacks and green in the tops. It had there's some very interesting transforms that you can do by giving the quote-unquote wrong target.
What you have to consider is because the algorithm kind of iteratively goes towards a result, when you don't explicitly tell it that it's a monochrome or bichrome image, there's always going to be a certain residue of color in it because it starts to dilute it effectively, but it's it's only going to be perfectly diluted in the limit of an infinite number of rotations. So then it helps tell the algorithm, okay, it's monochrome, then it will first manipulate the image, and then at some point it will reduce, because effectively there's another interesting thing is that you're working in a smaller color space, essentially, if you're working monochrome, because it's just on a line. Mm-hmm. So you explicitly tell it, work on a line, which means that it will remove all these kind of residues from the image. One of the things you start noticing when you look at like the difference between something shot on film, even in photography, is how much more vibrant colors generally look in digital. Not always, because Technicolor is obviously a bit of an exception, but generally, when you look at film, the images have less entropy. So there's more, you don't get these really vibrant reds and high saturated colors. You get a more muted look to it.
Right.
So I used this, which was a really nice picture from Rome. It's got plenty of color, but it's not as high saturated. It's just got this much more. Somehow it feels more. It doesn't strain the eyes as much as digital images tend to do.
Yeah, exactly. Yeah, it's got this muted color palette.
You try to get this kind of more muted palette out with and obviously there's another thing happening here, which is the fact that the original image was kind of shot more during, it's also kind of late in the afternoon, but this one is clearly going more towards sunset. So it tries to match that kind of look to it. But you can see that it kind of gets the more muted palette. So yeah, these are kind of nice kind of examples to play with.
Yeah, no, that's an amazing result.
So I have this photograph of this girl standing on a rock somewhere. Target. Very stylized, essentially. Dark and contrasty.
That looks like it's been shot in Cape Town. I'd put money that's in Cape Town. I recognize those trees.
In part, the challenges are with these kind of algorithms, because now the challenge becomes, so what's an appropriate target, essentially?
Yeah.
How do you select targets? What are the visual cues that are going to tell you that something is going to work and look good, or something is not going to work that well? So here you kind of get to say a similar kind of, it changes the, obviously it becomes a lot darker, and a little bit more subtle in terms of its color.
Yeah.
Yeah, so I think that's one thing where I think there's still work to be done, is how do you define a proper target? So what causes the algorithm to kind of focus on the wrong things, and what
this tool needs to come with a guide, and you really need to pay attention to the guide to know how to lead it in the wrong direction, or lead it in the right direction, or what I mean by lead it in the wrong direction is to come up with interesting results, unexpected results, by pointing to unexpected targets.
Yeah, I think that's the thing, and in a way, there's a certain obviously the algorithm looks differently to the image a human would.
Right.
So you kind of have to kind of see it through the eyes of the algorithm, the image, and see what is it going to do with this image. So why does it do it in this way, so to speak? And this is often related to the fact, because one of the first things people ask me is, okay, I have this shot of this person in a room, and then I have a counter shot with back-facing light against the window, and then they expect that to match. But then I say, okay, but these two images are, in terms of stimuli, they're completely different. Okay, they might have been shot in exactly the same spot, but one is against a blue wall, the other one is against a gray sky. This is not the way an algorithm looks to an image. It's not, to us, it's kind of trivial to see, okay, these are the persons, but the algorithm expects the same stuff to be in the frame.
Right. Okay, so yeah, I think that's a good segue point into the visual cognition part. Now, let me just give a little bit of background. I'd say that firstly, I'd encourage people to go and look at the 2 episodes that I did with Troy if they don't understand all the ins and outs of visual cognition, because that's
I saw it.
it's a world unto itself. But in summary, I'd say the human visual system is highly plastic and adaptable, and in many cases, the same stimuli can appear totally different because of the context of how it's presented, spatially and over time. So somehow you got onto this deep black hole. What was your entry point, and where did you feel that this was necessary to tackle?
It started with Troy badgering me about visual cognition and this, and at first I thought, So it took a little while for it to sink in, essentially, for 2 reasons. One is that at first I had a lot of difficulty kind of. I saw all the examples, but generally found them very. So I had for myself, I had to kind of visualize. Okay, are these examples of extremes? So in other words, the image has deliberately been pushed to highlight a certain effect, but it's not going to. How is this going to affect something in reality, so to speak? So these examples are quite specific, so to speak. So, and when I look at an image of a film, a real film, a natural image, these things are going to be a lot more subtle, a lot more. So how am I going to translate all these effects that you're showing to me, which I think, okay, I get that they are there, but to what degree do they affect what we see every day, so to speak? And this initially my viewpoint was, it's kind of on the outer edges of, it's not that important, and I've kind of moved away from from that towards actually it's in everything we see and we do. There is no absolute color there. I'm kind of a convert now, and he's ruined me essentially.
Yeah, exactly. But I mean, okay, let's just say before we dive completely into all of this nonsense, how does it affect the matching project? Does it feed back into that project in any way?
It affects us to a degree. So I've been kind of thinking about how can you incorporate visual cognition effects into that. But at the same time, there are elements in the color matching algorithm where I say, okay, if I take two exactly the same images, for example, where the kind of first simplest case where I match a grade, then I know all the context and all the pixels are going to be the same. So under those conditions, you wouldn't expect visual cognition to change the way we perceive the image, because effectively the distribution ensures that everything is in the right place. There's not much room for error in terms of where you can place color, essentially. So, and I think the further you move away towards a more generalized view of an image, where you try to match something which has absolutely no connection to each other, that's where I think the maximum effect is going to be of the visual cognition. Because and this is kind of where I get back to the whole question about picking the right targets, is that what you have to do is not only look towards, you have to have similar context. So when we say an image looks similar, that's because not only does it feature similar stimuli, it features similar stimuli in a similar context. So, and under those circumstances, I think visual cognition is going to have less of an effect on the outcome. I think there are certain things that can be improved in terms of, as we say, I did some experiments on it where context plays a role, and I think that in general can produce more visually appealing results. But I think in general, the whole assumptions about that underlie the algorithm, where you say I have to have a similar setting with similar content. So I have buildings, I have trees. I think that's going to not be affected that much by visual cognition, so to speak. It's really going to come down to detailed effects. I mean, I put some comparisons on a Discord server where I tried to see, okay, if I do a color match, how well can colorists separate the original grade from two matched grades? And two things were, good for the colorists is that they, on average, more people picked the right one than the wrong one. But at the same time, good for the algorithm, they didn't all pick the right one. So some people were fooled in brackets. And I think also one of the things I had a nice discussion with Ken Shin about this, where he said, in essence, we're not looking for exact matches. We're looking towards something that visually looks good. And sometimes what visually looks good is not essentially the perfect match to the image, which I think is where the variation comes in, and you start to make creative choices in terms of, well, this is supposed to look, this just looks better. I don't care if it's a better match on some theoretical scale. Colorists look for pictures that look good. They're visually appealing. And so other elements come in that do not have anything to do with is the exact luminance in terms of some theoretical definition being met. So I think that's where kind of the difference start to come in.
Right. Okay, so let's just take a step back. You've separately developed a tool that basically looks at one image. It's not a before and after situation now. You're looking at one image to see spatially how gradients of either color or brightness or various stimuli change across the image. And then based on, I mean, have you made a certain link to the human visual observer and those sensitivity curves to know what things to highlight more than others? How have you linked back to the human observer?
Well, this is kind of where I always work. So I read papers, but I only really understand stuff and if I kind of program something for myself and get to understand it in my own terms, essentially, because that's just the way I work. So I started thinking about how can I kind of make a more abstract version of this, which doesn't really involve a very mechanistic approach where you try to exactly replicate what the visual system does. But I do try to kind of replicate the results that you see, the effect of cognition. So, and then I started seeing, okay, we have all these different things like simultaneous contrast.
Yep.
We have effects like assimilation, which kind of seems counterintuitive because it's completely opposite of simultaneous contrast, and these things are happening at the same time. And then you have this affair, the watercolor effect, which introduces color, which is not there essentially, which is not in the stimuli at all.
Yeah.
It's just white, but we don't see white, for example.
Yeah, neon spreading's the same. You have thin lines, but we see a whole clump of color. Yeah.
Yeah. So and then I started thinking, so how can you model this in an abstract fashion, more or less? And I very quickly came to a kind of kernel-based approach, which is kind of I started off with simultaneous contrast because that was the obvious case where you said, okay, the stimuli is gray, but I'm seeing blue or I'm seeing yellow depending on its context. It was also very obvious that whatever happens is the opposite of the context essentially. So the brain appears to be kind of performing a form of image enhancement, edge enhancement, but not just edge enhancement, but it just tries to enhance the differences between colors that are there in the stimuli.
Right. So
this was kind of the basis for it. And then I built a model for lateral inhibition, which was just based on a kernel. A kernel is kind of so if you go, for example, to image smoothing,
right,
what happens is you smooth it by averaging over some area around.
Oh, like a blur kernel. Yeah. Okay. Got you. Yeah.
And this works in exactly the same way. So the way I define context is it's some kind of average of the area around the pixel, and you define a kernel, which is the way you average that thing, and what weight you give every pixel. And then you have to get the question: oh, does it need to be short range or long range? Well, a lot of these effects appear to be pretty long ranged. So you pick a kernel which has a fairly long range. Such that information from other sides of the picture are not included as heavily as things that are near, but they are included. And then I effectively said, okay, so the simultaneous contrast effect kind of represents the difference between the pixel value and its background, and that's kind of added to the whole to kind of get a final result. So that was the first version. Obviously, it's gone through some let's say iterations and improvements and all kinds of stuff.
Right.
And then I started looking at, okay, what's assimilation? Assimilation is a form of blending, colors blend, and then you can have a discussion whether the blending is a physical limitation of the eye, so to speak, where you say, okay, kind of like a resolution effect, where you say, okay, the light comes into the eye, but at some point our eyes cannot resolve the details, so we kind of get an average over that area, or as Troy would argue, all things that happen in the visual system are kind of done for a reason. So there's method behind the whole behind the madness.
Yeah.
But inherently, it doesn't really matter to the result. So effectively, I've said, okay, assimilation is a form of local blending. So it's much more short-ranged, although it depends effectively on distance. The more distance you take from an image, the more blending of a larger area you're going to see.
Okay, so now I understand why you had to factor in viewing distance, essentially,
exactly,
optical resolution. Yeah. Okay, I get it now.
So I treat it like a resolution effect, even though because you might say, okay, another way of looking at blending is, and then we get kind of to the whole point about the watercolor effect, is I think it's pretty obvious that our visual system uses a very efficient way of processing the data. We do not use all the data that is presented to us. So essentially, our brain compresses the information before it starts to form the picture into kind of the most important elements. Because if you want to, it's kind of amazing to think that our brain is able to perceive, to work with so much information. If you see what comes into our eyes in terms of signal, in terms of resolution, in terms of the amount of data, it's pretty amazing how quickly we are able to adapt to the best computers in the world cannot replicate this kind of incredibly fast processing and all the higher order stuff that we do with it, which is where kind of I think the whole idea of color. This is where I think Troy kind of color with the big C and color with a small c.
Right.
So you can view color as kind of a signal, but you can also say, okay, but color is also something that we assign to it. We say this object is red and this object is blue, and I think that kind of happens at a much higher cognitive level. But you can also look at color just what is the signal that we interpret essentially? And it's obvious that we do not see a gray center stimuli if you're surrounded by a yellow context, so to speak. So then the process signal essentially becomes a kind of bluish color with a small c, even though we don't assign color to it. It is kind of the building block for what will later become. It's the building block of the picture formation essentially, and you need to do some pre-processing to the raw stimuli signal to get to a better representation of what will ultimately become the picture.
Those differencing signals that happen very early in the retina, they're doing a big what you called compression to filter out, say, okay, I only want to know the differences, and hence I'm going to make assumptions from that. Yeah, rather than actually being, the typical thing that Troy mentioned, it's not like it's a camera and it's actually sending information up the thing. No, it's sending like useful summaries of what it's roughly seeing, and then the brain fills in the gaps.
Yeah, and I think that's one of the interesting things of the watercolor effect. Was the way I modeled the watercolor effect was to simply say, okay, I have this picture. I think, and that's what I'd say. The whole idea of assimilation is compression is easier on smooth results, because essentially a way of blending is a way of compressing the information into less colors effectively.
Yep.
So you could say it's an effective technique by the visual system to reduce the information before it's being effectively compressed, or before the most important features are taken out. So in the way I modeled what the watercolor effect is to simply say, okay, obviously gradients are really important in our visual system, and our whole system is kind of tuned to see high gradient areas, because that's where most of the information in the image is. And I simply assumed that, okay, well, if I want to model the watercolor effect, I have to effectively say, okay, everything beyond a certain threshold of gradient information is seen as important, and everything else is kind of seen as very much less important. So we have a high sampling rate in the high gradient areas, and a very low sampling rate in the low gradient areas. And then in the picture formation stage, we kind of fill in the blanks, and this is what causes color to appear in areas where it's not in the stimuli, because effectively the area where there is no that's white is stored in a much more compressed or processed in a much more compressed manner, and then we kind of fill in the blanks, and that this leads to a kind of color bleeding into that area as a consequence of, and then you have to question, is this a deliberate, is this kind of a side effect of the process, or is this a deliberate effect where it's also useful in an evolutionary sense, where there's color where it didn't used to be? Does it help us to differentiate, for example, between different forms? And I think you can have a discussion about that. And could be one, it could be the other, it could be a combination of both, essentially.
Yeah, segmenting of forms based on a boundary being the difference, being the most important thing, is weighted way higher than the difference within a form. Yeah.
Yeah, and I mean, so in this way, so I made this model in a sense to kind of get a handle on it from my own perspective.
Right.
And at the same time, try to do something which is has some kind of utility to it, in the sense that it can give a relatively quick result, such that it might be incorporated in some way in some tool, or to again give a better kind of. So it would be nice to kind of get an idea for a colorist to see kind of what does this visual cognized color distribution look like next to the one that I'm actually have to, because the thing is, you're looking at the picture obviously and doing it, but you only have to stimulate to manipulate.
Right.
To form the picture. So you're kind of working in two different spaces. You're seeing something different than what you're working with. And this in of itself is kind of an interesting aspect.
Yeah, I mentioned to you before, like how you present the results is very interesting, because if you present them multiplied or added on top of the image, then your brain actually just takes that as the new starting point and adapts further. Yeah. So it's very interesting.
Yesterday, because I think I showed those images with those gradients that you put up before.
Yeah.
Because I started looking for ways of how can somebody match cognitively what they're seeing. Now, one difficulty that I saw is you essentially can't. You cannot match. You only see relative. You cannot match. There's no absolute color essentially. So you cannot absolutely match to a visual cognized color by saying, okay, I'm going to make this. So you can only match it in perception, so to speak.
In context, in the moment.
Yeah, exactly. And so the one thing that you, and then you have also the fact, which I think Troy, you spoke a lot about in the stream that you did with him, is the idea of the increment-decrement problem, that increment and decrements essentially represent separate color spaces. They just look different. No matter what you do, you're not going to be able to have an increment match a decrement. A decrement is always going to look dark, and an increment is always going to look light to our eyes, even no matter how much you manipulate it.
Right.
So this also means that in matching, you have to kind of replicate this. You can only match increments to increments and decrements to decrements. That's effectively the and there's a kind of there's this line where one goes to the other, but they're kind of like separate universes.
Yeah, I mean, think about this. Just, I mean, I don't know how involved you are in some of the recent tools that have come into Resolve, but something that's come in now is a Z depth keyer. So basically, it can work out what was how far from the camera, and it can give you a black and white matte with a grayscale gradient in between, and you can put different colors in the thing that was close to the camera versus different, and you can add extra separation. So what if your output, which is this important areas or things that our differential signal is really high, give that back to the colorist, and then we can do things in that area. For example, sharpen these parts even more because we really want to highlight the eyes or highlight this or highlight that.
I think this is really where the interesting kind of questions are. So how can you apply kind of the know-how that you have about, and I think this was kind of the whole deal with the picture formation thread, where you kind of got to figure how can we know a lot of these things, but how can we use them in an effective way as colorists to kind of get a better picture essentially. And that I think is where at this point it's just descriptive essentially, trying to predict what and then you have to think, so what do these numbers mean? Because I already realized yesterday, okay, so they don't mean in anything in an absolute sense. You can only use them in a relative sense, again, to match. So this is kind of where I'm at now. If you do matching between colors, I can only show the success of the method by matching in context, essentially. And then you can compare them. So that means if you do experiments, and this is something really interesting because I read a lot of papers on people doing experimentation on matching visual cognition to stimuli, but they always perform some kind of so it seems like there are some errors in the way that these matching experiments are performed, where they're trying to match increments to decrements and all kinds of stuff. And I think if you want to do this, there are some really strict constraints under which you can perform such matching, which are, like I said, you can match a decrement to a decrement and an increment to an increment, but matching increments to decrements, I think, is going to screw up your model because effectively these two things don't look the same to us, and you're introducing a kind of noise component. Which tries to force something on top of something that's not matchable effectively.
Yeah, I mean, you're talking over and above, for example, only within a 2-degree field, or only in a certain controlled environment, or only once you've stabilized for 20 minutes in that environment and settled your vision. You're saying
exactly.
within the presented frame.
Yeah, but then the thing is also the colors just look different. If you have an increment color, it's just different from the decrement version of that same color, and no matter what. And then there's an interesting question: so what's in between? Because what you see if you make a gradient. So I attempted to kind of I made this image of squares in a gradient.
Yeah.
And the squares go from dark to light, and the gradient itself behind it also goes from dark to light in a different direction. What you get is, of course, you get the simultaneous contrast effect. So bright colors become even brighter and darker colors become even darker. And then I have the algorithm where I can kind of reverse that effect to kind of say, okay, given I try to estimate what would stimuli look like without the simultaneous contrast effect. But then an interesting thing happens. This kind of works up to the limit of increment and decrement. And then there's this kind of switch. Where you have this narrow band where there's kind of a no man's land, you might say, and the colors look literally different. They look dark on one side and light on the other side, and within their own environment, they're all kind of consistent. You can say, okay, the algorithm has succeeded in matching all these different relative likenesses to each other such that they are very similar. But there's this magic line of increment decrement which separates these two universes, and that's a really interesting effect, and the question is what's in the middle. So what's exactly on that middle level? Because you might say, okay, what is assuming a kind of thought experiment where you're standing in front of a color screen which is infinitely large, an infinitely large red, such that there is no context. How would our brain interpret that? What does that represent? Does that represent the kind of color that color scientists talk about when they create a kind of lab color space with all kinds of rules, so to speak, a kind of
Hmm.
theoretical. Because I do use although Troy absolutely
I
despised this.
saw you got into trouble. I saw it.
I, I use the perceptual color spaces because they do that, at least to me, they do seem to have some utility, but more as like theoretical limits to something than really that it represents something that we actually see, so to speak.
I mean, you do have to have some working model, but yeah, the nitty-gritty of it, it's definitely above my pay grade. Both the projects, whether it's the visual cognition side or the matching project, applied to noise and texture, I think could also be another thing. I mean, it's some trick that they used to do in the age of DVDs is prior to, you had your film originated on film project and you were about to make it into a 720p DVD, you'd put heavy noise reduction to kill all the high frequency,
Yeah,
such that your limited bandwidth in the DVD would be used on important picture information and nothing would be wasted on the noise. So just I've been, whether it you adjusting the MTF, the sharpness contrast, the contrast for brightness to sharpness. I've been yearning to have a tool that essentially can do Fourier analysis on the signal, give me controls over the different frequency ranges, and then, yeah,
yeah.
make certain adjustments. So I think both of these tools are very interesting moves in that direction.
Yeah, thank you. I think well, one of the this is the thing that you see also in digital streaming because there the same thing happens. You smooth the image such that effectively noise is an issue in compressing data
Right.
because it essentially makes the compression all the more so a relatively light bit of noise reduction will make you able to compress the image much more.
Mm,
So you might say that it's actually more effective from a visual perspective to for a streaming service to smooth out the noise and add some grain back in the kind of processing part to make it visually appealing because then you can kind of really purists obviously hate this kind of idea, but
right.
from my data compression perspective, if you have a very good compressor that can keep the detail and we have so much discussion, the image is in the grain. The grain is the image. This is kind of the
Right. Okay. Yeah. Well, that's a whole. You just stepped on another mine. I'm sorry. Boom. Okay. Well, okay. Just to really give the purest nightmares. What if the LG TV or the Sony TV has its noise, which it puts back? So
yeah, exactly. So the ideal kind of cheat would be to kind of completely remove all the grain, compress it very heavily, and then put it back the grain way at the end when it's being kind of transformed back to the picture you see in the to the screen, so to speak. And the question then is, do people see that? They obviously will hate it if they know it,
yeah.
but if they don't know it, that's the real trick. So what's the difference between the image? If you can't see it, it doesn't matter essentially, which is what.
Well, how about this? You have 10 like filmmaker sanctioned preset grains, and you can apply as the user, they're on your remote control. You can put them back in.
Give me that
I want,
70 high grain look.
right.
Well, that in itself would be really cool to have, by the way, to kind of in a TV have settings where you can literally apply a LUT to a movie and get a kind of I want to see this movie in a kind of set 70s gritty way and have some kind of predefined LUT settings that the film that is used at grain at but then obviously in a way that actually looks good.
Well, I mean, it might be a way to reinvigorate our industry. We're just going to send you the raw scene referred thing. We're going to send you the raw. It's balanced. It's everything. You apply a look of your choice. This is the recommended look, but you can choose. You can put the Titanic on Transformers, or you can put the. Okay, we're getting into the extremes. Um, yeah, Menno, thanks for your time. I think this has been an amazing chat, and this is really is the. Let me just put one last spin on it. I mean, I planning to do some research that might be linked to a master's later in the year. I could see that both these tools could be the underlying tools which I take into some research, an analytical research project. So I think there's whether it's in the industry actually doing jobs or whether it's in a theoretical analysis point on vision or on production in general. I think there's a huge future. So thank you very much for all the hard work you've done. And yeah, I'm very keen to help you in the process of testing and.
Thank you very much. Thank you very much for having me on the podcast. I think it's really nice that. Well, first of all, I really like the podcast and all the. I mean, I've seen a few of them, and I thought it's really instructive to kind of
thank you.
get these people's perspective. Also, in the meantime, learn a lot about color and the way colorists look at images. So yeah, well, like I said, I'm really happy to that I've been able to give them the opportunity to talk with you.
Yeah, no, definitely. There's a perfect example. I mean, if this reflects back to our open source versus closed source discussion, at face value, I was skeptical, and when it didn't do exactly what I thought it would do, I said, wrong. But no, actually, on deeper inspection, there's way more applications for this kind of analysis. So yeah, I think that's it's been very instructive to me.
Yeah, thank you. That's also instructive for me because let's say the one thing that I've discovered is that you pick a few images from the internet which are heavily compressed, and you can't really get a good feel for what it's like to work with a proper image which is not formed, so to speak. And I think that was a really insightful thing to see. Okay. There's a lot of things I've assumed which are not the reality of or for a colorist or from somebody working with actual footage that comes from a camera and all the steps. That's what I'm looking at is formed pictures, and that's a different ball game altogether, so to speak.
Yeah, and then when we put the whole thing of client, it's actually client. What we do is actually client service. You know, there's that whole component, what the client's asking for, and how we do that dance. Great, man. So thank you so much for your time.
Thanks a lot. And
cool.
We'll speak to each other soon.
Yeah, definitely. Well, keep those forums burning. Thanks again for listening to the Color Mentor podcast. I hope you enjoyed it as much as I did. You can leave comments on Patreon or Instagram. The Instagram handle is color.mentor. And remember to head over to Color Mentor page on patreon.com and check out the goodies there. We'll see you next time.